Hello, this is the presentation I gave at your convention in Calgary on May 13, 2019. The topic that I want to talk about in this presentation is about velocity model calibration for microseismic monitoring purpose. You may heard of people saying that your microseismic is only going to be as accurate as your velocity model. So in some sense that the accuracy of your velocity model controls the upper limit of the value that you can expect from your microseismic investment. So there's a reason to make it as accurate as possible. In oil and gas industry, most microseismicity occurs in the shale formation or the tight sandstone where anisotropy is evident. So the question is, how are we going to calibrate an anisotropic velocity model for the shale formation? The idea that we tested and developed in this case study is the so-called controlled complexity, and it works in this example, and that's what I want to share with you in this presentation. So velocity calibration in a nutshell is to find the model that best match your data. So first of all, I take a few cartoons from this website just to highlight the problem. It's a super simplified version. The data points are the black dots. It's in 2D. So they're all the same. The data points are the same. The red curve is the model. And as you can see, they're all different. So the question is, which one would you pick? Or make it sound more serious, which vendor's model would you like to pay? If you hear the argument, they all make sense. For example, the linear regression, right? It has the minimum features that I enforced on my model. It works in most cases, so it works here as well, as you can see. The other vendor may say, I have a sophisticated algorithms that not only captures the global trend, but also capture the local trend of your data. So this model should best represent the data. The other vendor may come in and say, you shouldn't look at a single model only. The model should be a range of models within this upper boundary and the lower boundary. So they all make sense. So without any constraint of this hypothesis, the number of models that can fit your data is infinite, as you can see in this cartoon. And this is just a 2D problems. For velocity calibration, it's a much higher dimension problems. So we can do a simple math. This is a screen capture I took from this project that I'll show you. I'll show the details later. So let's just assume it's a layered model, and each layer is anisotropic. So 14 layers. Each layer has 5 degrees of freedom. VPVS and 3 Thomsen parameters. That will give us 70 dimensions. And if we have 12 calibration shots, which are captured by 12 3-component geophones, if we count both P and shear wave, we're going to have about 200 to 300 data points. Right, so you can imagine that you have 300 data points maximum that in a 70 dimension space. So how sparse the data points will be and what kind of algorithms you would use to get the model that best explain those data in these high dimensions. So the ideas that we have is we have to use some domain knowledge to constrain the space of the hypothesis to guide the algorithms to get the best model that consistent with your understanding and consistent with your domain knowledge. And that's actually the message that I'm trying to convey, is your experience and your understanding of this field have to take the driver's seat and has to guide the algorithms to get the best model. And that's the idea behind the controlled complexity. And the specific examples that I show here works really well in this case studies. And I believe the same thing will happen for a different project, but you may have some variations. And I'll talk about those in a moment. So in the following slides, I'll basically introduce you the background of this project, and then I'll spend most of the time on the 2 stepping stone. One stepping stone is the ray tracing. I didn't show it here in this slides. The ray tracing is important because we are looking at a strong anisotropy, because the Thomsen parameters, we don't want to have a narrow range. We need to have a relatively large range, and when the range is large, it's not going to be necessarily a weak anisotropy, so we should have a ray tracing method that can take account arbitrarily strong anisotropy, so to speak. The second step is this inversion. So the stepping stone that we used, the algorithm we used, is the Gaussian Particle Swarm Optimization. It doesn't have to be this specific algorithms. Any non-local minimization algorithm will do, and I'll talk a little bit more why I picked this one. And once we have these two stepping stones, forward modeling and inversion or the optimization, the workflow is really simple. The first step is to build isotropic velocity model, so it's a relatively low dimension and within very narrow range. Basically, the range is to cover the error, the uncertainty of the sonic lock, and then we add Thomsen parameter, and it's a constant Thomsen parameters, so that's at 3 dimensions. And after that, we allow the Thomsen parameters to be depth dependent. So the Thomsen parameter will be a constant value that we get in the second step, plus a factor times the auxiliary log. So the auxiliary log could be any logs that you think capture the anisotropy, the degree of anisotropy. It could be 1 over VP, it could be gamma log, it could be any other measurement that you have, you believe captures the degree of anisotropy. So up to here, and the last step is now we allow each layer to have 5 degrees of freedom, and they vary independently from the other layer. Some of the variations here you can play with is you can either update all the layers all together, or you can update the layers 1 layer at a time sequentially or randomly, or you can say I want to update the 3 layers at a time, because they're consistent, they're close in space. So when you want to increase them, all of them has to increase at the same time. So those are the variation, the hyperparameters that you can tune in this algorithm, in this workflow. The processing results, we evaluate the processing results by a few things. One is, of course, the residual. So the travel time residual, which is defined as the theoretical arrival, subtract the observed arrival. So that travel time residual has to reduce, at least it should not increase. And then we also use that velocity model to process the whole data sets and look at the spatial patterns of the data sets and evaluate the effectiveness of these algorithms. So it improved the events cloud interpretability, reduced the artifact, and the last thing improved the slow shear wave arrival time, predictability. That's come as a little bit surprise, so I put the exclamation mark here. When we are calibrating the velocity models, we didn't look at the slow shear wave arrival, because only 1 or 2 calibration shots has a clear slow SV wave arrivals, or QSV wave arrivals. We didn't use those travel time for the velocity calibration, but once we go through all this workflow and use the model to calculate the theoretical arrival, we notice inconsistent with the SV wave arrivals. So that kind of increase the confidence of us on this workflow. So here is the background of this project. It's a horizontal treatment, hydraulic fracturing. The different color represent different stage from toe to heel. We have about 12 stages, and we have a string shots at the lower corner, and that's actually the only shots that we know the location. The observation boreholes is very close nearby. It's actually another horizontal drilled boreholes, so probably it's going to be used for a different treatment. We don't know, but the geoforms is along the vertical part of the wellhole. It's very close. The black curve is the sonic lock, the P-wave sonic lock acquired along the treatment well. So it's very relevant till this depth, right? And after that, we don't have data from the treatment well. So this bottom sonic lock is actually coming from nearby well lock. So the velocity, you do notice that there is a velocity increase below the target zone. There are a few challenges in this project. Number one is there's only, as I said, there's only 1 shot with no location, and it's not a perforation shot. The completion method is sliding sleeve, so there's no clear bar job events that we ever recorded. And the other thing is there's clearly a shear wave splitting. I just take a cropped of these pictures, and you can see the blue curve is the polarized, horizontal polarized wave, SH wave, and the black is the vertical polarized shear wave. So you can see that there is a slow shear wave arrival along this way right after the SH wave arrival. So that's shear wave splitting. You have to take the anisotropy into account. So to address those questions, the first one, we use early microseismic events from each stage. So we correlate the occurrence of the microseismicity, the time of that, with the injection schedule. And we pick those ones that occur at a very early time of injection, and we assume those events are at the location where the injection point is. So it sounds easy, but it takes quite tedious. And my colleagues actually published a paper based on that. Manually select some of the early microseismic data and use the synthetic data to verify those events are actually coming at the injection point, not at the shallow part. And you remember, we don't have velocity yet at that point. So it takes some effort to do that, and in this work we actually use the same calibration shots as we used in the previous study. And the ray tracing method is we have to account the strong anisotropy, not weak anisotropy. So the Thomsen parameters that you usually see on the left is based on weak anisotropy. It's not going to be used. We have to use the general equations on the right. And here I just shows you an example of the two-point ray tracing that we developed for this project. QP and QSH are fine. There's only a body wave. We didn't include any header wave in this picture, but we can do that. Then the most interesting is this quasi SV wave for a given pair of source and receivers. There's multiple arrivals, and that's why you notice these triplications. You don't need strong anisotropy to have triplication for SV wave, but when the anisotropy is stronger, you do notice those things. But the good thing is we didn't use SV wave for the velocity calibration. We use SH and the Q wave, but we can predict the theoretical SV wave if we need to. So that's the first stepping stone. The second one is the inversion, and I choose this non-local minimization method called Gaussian Particle Swarm Optimization. It's a variation of the conventional particle swarm optimization. The reason I choose this instead of the traditional gradient-based method is because everyone should probably know is the minimum, local minimum. So the picture on the left shows you the error space in 2D. Blue is low, and the middle at the center is the global minimum, and the red is high, and we are looking for the global minimum in this example. The right shows you the same picture but in 3D to highlight the topography of this region. So you may know that a gradient-based method, those local minimization method, as long as your initial point is not facing the valley somewhere here, then you are likely end up in those local minimums. So that's number one issue, that I don't want to use the local minimization method. The other reason is, actually I quote from this paper, a deeper and more profound difficulty originates from the proliferation of saddle points, not really local minimum, especially in high dimension problems. So we are looking at a high dimension problems, not super high, like 1 million dimensions, but 70 dimensions is really high. In those dimensions, local minimum is not that scary. The saddle point is more severe in this case, and if you look at the gradient, in the saddle points, the gradient vanish. So you're not be able to know which direction I should go to further minimize or look for the global minimum. So that's the reason we choose the Gaussian particle swarm optimization. The theory is relatively simple based on the paper in 2004. Each update is based on this equation. Xi is the position for one particle, and Pi and Pg is the best performance, the best position of one particle and the best performance of all the particles. So in this example, I throw in 50 particles, as you can see in this picture. So they work as a team. And each update is the combination of my best performance in the past and the team's performance. And based on this two, the combination of these two, each particles will be updated in the direction based on this information. So it has some memories about the topography. Unlike the single agent method like stimulated annealing, you're only looking at one point at a time, and you don't have the memories of the places you have been visited before. So that's the motivation that we choose this Gaussian Particle Swarm Optimization. Here I have a video to show you the iterations of this method. I throw in 50. By the way, the blue is the local minimum and the red is global maximum. And in this example, I'm looking for the global maximum or the global optimum. And you can see after 5 to 10 iterations, all the particles pretty much, there's at least one particles already found the global maximum, which is at the center. And in the following iterations, there are a few particles they're not settled yet. They're still exploring the error space, and probably about 60 to 80 iterations, all particles agree that's the best point that I can find in this error space. So in practice, you don't have to wait till all of them converge. In practice, you probably just wait, give it 5 or 10 iterations, and at the end, you just output the global, the maximum, and at a very high probability, depending on the number of particles and the cases, you have a high probability that that point is a global optimum, or very close to the global optimum. So that's why we choose this optimization method. The following is relatively simple. The first step is to use this method, but build an isotropic layered model first. In this example, we designed a 14-layered model based on the sonic log, VP and VS, and the range, as you can see, I'm not sure if you can really see the range, is very narrow. So that's the range that basically to account for the error of the sonic log. You don't want to have a large range because otherwise your model will try to explain the anisotropy in the data by your isotropic model. So that's a bias that you don't want. So that's why we have a very narrow range. And using GPSO optimization method, we can reduce the travel time residual from 14.2 to 3.45. So that's a huge, significant improvement because the initial model is just a mean value between those layers. And then we use this model to locate all the events. As you can see, this is the picture. The range is about 1.4 kilometers long, and that's the depth. So for the plan view, you don't see much differences across different velocity models because the azimuth is well constrained, no matter you're using isotropic velocity or anisotropic velocity, because we are only using the projection on the horizontal, the azimuth. Right? The vertical one is problematic. You can first see there is some linear trend, and this is kind of artificial. If you believe this is true, then your explanation would be there's some stress, discontinuity or stress boundaries here. So there's no, the seismicity becomes aseismic, and then the seismics again. Then you have to explain what is going on here in geomechanics model. Right? That's one thing. The other thing is notice this triangle shape, particularly for this green dots. Those regions are actually experiencing a high velocity because of the anisotropy, but you are using an isotropic velocity model, so those ones has to go closer to the observation borehole to explain the data, and that's why you have this triangle shape. This triangle shape is severe as you go up larger offset. It's not that significant when you go to the near offset. That's because you experience less effect of the anisotropy. Now the next step is now I introduce a constant 3 Thomsen parameters, and that's the result. By adding this 3 Thomsen parameters, the shallow linear trend is gone, but we see some other artifacts here, and that's related to the velocity layers. So as you cross the velocity layers, because the anisotropy is not correct yet, the travel time changes a lot, and because of that, the microseismic events start to align along those velocity boundaries. The third step is to add the depth-dependent Thomsen parameters, and we use 1 over Vp as the auxiliary log, assuming that a higher Vp corresponding to a lower anisotropy. If you have other measurement, like shear wave splitting analysis for different layers, you can actually use that information. It's more accurate than using 1 over Vp or even using gamma logs. And then what we can see is this very thin layer artifact is gone. The velocity, some of the layers are okay now, but you can still see a gap in between, and also the triangle shape is still here. And that's because the anisotropy is not correct yet. Now the last step is to allow layers to be independent. And what we are doing here actually is a combination of the algorithm and the manual adjustment. So the residual here actually didn't further reduce. It's actually the same value as before. But we are able to reduce the artifacts as well. And if you look at this triangle shape, it's much less. It's still some there, but that's the best that we could achieve within time limit. And you know that that's the Thomsen parameters that we got as the final output. So here is just a quick overview of what we did. The first step, by adding Thomsen parameters, we can reduce the shallow linearity, and by adding Thomsen parameters, make them vertical dependent. And finally, each layer is dependent from the other layer. We are able to gradually reduce the artifacts and make the locations more increase the interpretability. The triangle shape is less, and that's the other thing is, if you notice this golden layer, golden line, or brown line, this line, that's the theoretical SV wave that based on that final model, and you can actually see this wave arrival is consistent with this with this black line, and that kind of give us more confidence that we did get the velocity model. That's very we kind of increase our confidence of the velocity model. So here I can conclude this presentation. We built a vertical transversal isotropic velocity model for multi-stage hydraulic simulation. Using a ray tracing, which allows a strong anisotropy and use the Gaussian Particle Swarm Optimization. The controlled complexity idea is to add a strong regularization so that you can narrow the model, the hypothesis space of your model to the ones that is consistent with your understanding, with our experience by looking at microseismic data for years and years. Right? So we're not relying on the algorithm to give us the result. We're actually using, we build our own domain knowledge in the algorithm. It's very effective, as I showed you, that improved the microseismic location and removes the artifacts. It's feasible to use the early microseismic for velocity calibration. This is what we did. I think it's the first time we did. We have a project that has no perforation shots or a known calibration shots. So it demonstrates that we can, using a calibrated velocity model, using early microseismic events, and a natural extension of this work is why just early microseismic? Why not just any microseismic events? So that's actually, we can do that. We're just assuming the location is right and the velocity is not. So we update the velocity. And then once we update the velocity, we actually relocate the microseismic events and then update the velocity again. And that's the same idea as the joint velocity and hypocenter inversion. It's the same idea, and it's a natural extension to do something like that in a real project, and that will increase your velocity model and also at the same time increase the accuracy of your microseismic location. And the whole process, once you set the hyperparameters, once you set the hyperparameters, the whole process is easy to automate. So you don't have to manually do step 1, step 2, step 3. It can be automatically carried out by algorithm once you set the range and how you update the layers and etc. into this workflow. So with that, thank you for listening.